All right, welcome everybody. It's my good pleasure to introduce Yi from Salesforce AI. So you graduated from Stanford Stats Department, where when I did my postdoc there, I have several years overlap, and we talk a lot about research. So his research interest is mostly in foundational side of data science and machine learning. He's been interested in a lot of things. We got a lot of work published, areas like theoretical deep learning, as well as computation theory for reinforcement learning. So recently, he's particularly interested in building some understanding for transformer architectures, I think, and foundation models. I think everybody is probably interested in this kind of topics. So it's your floor.
Okay, yeah, I guess, yeah, thanks, Stu, for the very warm introduction. And yeah, super excited today to be here virtually at U Minnesota. And then apologies for not being able to make it in person. But yeah, super excited for sharing some of our recent work with you guys today. And yeah, so today I'll be talking about this kind of live recent work on, it's really kind of an effort of trying to understand how learning has changed, and then what are some new features of learning in this new age of foundation models. Okay, so yeah, so I guess, yeah, so throughout the past decade, we have seen many advances in modern machine learning AI, starting from image classification, and then we're all the way up to today, where we're all in this big revolution brought by large language models such as ChatGPT. Yeah, so I guess, there's many kind of advances in this, and then I like to argue that every major advance here involves some new learning paradigms that are either does not exist before or were not as widely adopted. So, and then, for example, for this image-net-image classification, this big success is brought by the use of deep neural networks. For generative models, this is done by a new training paradigm, such as adversarial learning or diffusion models. For AlphaGo, this is done by doing reinforcement learning. And then for this game AI, such as Librettos for playing this superhuman poker, this is done by the paradigm of learning equilibrium in games. And for achieving this strong performance in natural language processing, this is done by new sequence-to-sequence architectures, as well as this one specific revolutionary architecture called the transformers. And then finally, for large language models, this is done by combining the transformers with massive pre-training as well as human feedback. Okay, so pretty much all these new advances involve some new learning paradigms that are kind of not as widely adopted in the machine learning world before. Okay, so I like to talk about some new learning paradigms in large language models today. And to see why this kind of the paradigm I'm going to introduce is new, I'd like to go back and revisit what we're all familiar with in the classical paradigm of supervised learning. Okay, so let's say we take this problem of image classification on ImageNet. Okay, and then, for example, in 2012, this AlexNet achieved the winning solution for this contest. And then what they, learning-wise, what they did is this standard procedure where they have a model architecture, for example, this AlexNet, and then I'll use this f(x) theta to denote this model architecture, and then use theta hat to denote the trained model. This trained model is obtained by training this model architecture on a training data set xi, yi, I equals 1 through n. Okay, so after training, I obtain this theta hat. And I'll use this model to output a prediction on a new test example. And then these test images are supposedly to be drawn from the same distribution as the training images. Okay, so I'll have yn plus 1 hat to be the model evaluated on the test example, which is the xn plus 1. And if a model is good, my test prediction will be close to the true test label. Okay, so this is all pretty standard, right? What we see here is that this model f theta hat, what it does here is that it fits a prediction function. And then in an image classification problem, this prediction function is a function from the image to the label. Okay, it's a fixed prediction function. But now in large language models, there's a new paradigm that has emerged called the in-context learning. So what is being done in context learning is a little bit different. So for example, starting from the GPT-3 paper, what people has found is that large language models are able to do this kind of learning procedures in an in-context fashion. So for example, here's I playing with the ChatGPT, and I prompt the ChatGPT with apple corresponds to fruit, sofa corresponds to furniture, and then bird corresponds to a question mark. The language model gives me an answer of animal. And this is the correct answer in this case, because apple belongs to fruits and sofa belongs to furnitures. And then so what I want the language model to answer is like the category of the bird, and then the language model correctly answers the animal. Okay, and then you can have all sorts of examples like this. The language model can do more complicated problems such as sentiment analysis and all sorts of other problems pretty accurately. But you realize that this kind of the learning paradigm is different here, because so first of all, we're playing with this large language model's data set, and this large language model is pre-trained on massive text, not just this kind of task, but also all sorts of tasks combined, or even like just text from the open web, okay, and massive amount of text. But now what we're doing here is that we're prompting it with a new task that the language model may or may not have seen. And we're prompting it in the format of we feed this training examples xi, yi equals y through n, combined with the new text input xn plus 1, and we concatenate all of these into a sequence, and we feed this as directly as the context input, as a prompt into the large language model. Okay, so in the example I just discussed above, described above, this x1, y1, x2, y2 corresponds to these two training examples, and the x3 corresponds to the test example I wanted to answer. And then the language model is going to give me an answer y hat 3, okay, which is this prediction on this new task. So this is a different function from the image to label, from the standard prediction function, right? So a natural question here is that what kind of function does this LLM fit in this setting? Okay, and then note that here, if you ask me the question of what kind of function is GPT-4 fitting, the answer will be necessarily kind of like there may be not a single satisfactory answer. The GPT-4 may be simultaneously doing like many things. But in this, at least we want to understand in this specific kind of task, what function is this GPT-4 fitting in order to do these tasks well. Okay. And a similar paradigm, you can also use a similar paradigm to use the language model to do reinforcement learning. So here's a reinforcement learning example. I'm playing this, I'm trying to play, I'm playing with the GPT-4, and then I'm trying to play this simple bandit game, multi-arm bandit with 3 arms. And I give it some initial prompt. It is fairly long, so I omitted this, but I'm just describing, hey, you're in the bandit game, and then you have 3 arms, and then your goal is to maximize the reward, and so on and so forth. And then, after seeing this prompt, the language model says, let's begin, and then it chooses arm 1 in the first round. I give it a reward saying, for arm 1, the reward is 0.5. And then language model in the second round chooses arm 2, I give it a reward again. It chooses arm 3, I give it a reward again. My reward is 1 for arm 3. And then now, after seeing all the 3 arms, the language model says, okay, so based on the current information, I'll choose arm 3 again, since it thinks the arm 3 has the highest reward in the first round of trials. Okay. So mathematically, you can also think about this as some sequence procedure where the language model begins by choosing an action A1. I give it reward 1, and then in the second round, it chooses A2, and then I give it R2, and so on and so forth. And then this procedure can last, indefinitely. Okay, I didn't try how it does like after this. Supposedly, it may be doing something smart, since already seeing already we can see from this round 4, it is choosing the arm that achieved the largest reward in the first 3 rounds. Okay, we don't know if this is like the cleverest thing. Like I don't have enough sample to tell like whether this is doing like some really smart thing, but at least it's doing something reasonable. People have been using the language model to do like LLM agents, and in my opinion, these LLM agents also follow a similar paradigm. Okay. So here's an example of an LLM agent procedure which is this simple act only paradigm, which is like a precursor to for example, the popular React framework that people use for agent problems. So in act only, what is done here is similar, right? Like the language model is responsible for taking actions. So action 1, 2, 3, 4. And then after they take the actions, we're going to follow the language model, and we actually take these actions in the real world. And then we feed these observations back into the language model. But then the language model is going to be the main thing that's responsible for giving me the next action. So mathematically, you can understand this as a sequence of actions and observations. So A1, O1, A2, O2, blah, 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 until the problem is solved. Okay. And both of these examples fall into this kind of more unified setting where, okay, again, you have this pre-trained LLM theta hat trained on massive text. But now both of them fall into this unified setting where what the language model does in this case is that it is given a new environment. You can think of it as a reinforcement learning environment like an MVP. And then the language model is fed with a sequence of histories, observations, actions, and rewards, and then up until time t, up until the observation at time t. Then given this input, the language model is responsible for taking the action at time t. Okay. And after the language model takes it, we can do this action in the real environment, and then we can observe the reward and observation, which can be used to feed back into the language model to do the next step. Okay, and then we can ask the same question here. In this case, what kind of function does this language model needs to fit in order to do well for this kind of tasks? Okay. Yeah. So I think like both of these are interesting questions, but of course we'd like a little bit of more controlled experiment to study this kind of question. So we begin with this specific question that has been studied in the literature. Can transformers really solve linear regression in context? Okay, so we want to pick a task that is controlled, and we can understand the performance of the transformers precisely in a quantitative fashion. So we pick linear regression, which is a standard task in machine learning, and see if transformers can at least solve this task well in context. Okay. And to explain what I mean by using transformers to solve linear regression, I'll give the setting. So for linear regression, I'll have a bunch of data sets called D, and each data set, the data sets are indexed by J. So each DJ is a different data set. And for each data set, it is going to be a sequence of length n+1, where it consists of xi, yi pairs I equals 1 through n+1, drawn from a linear model. So yi equals xi times w plus noise. And then this W is going to be the same for this entire sequence, xi, yi's. Okay, so all of these share the same W. They're generated from the same linear model. But the important thing here is that for different instances, I want that these different data sets be generated by different Ws. So if I draw a second data set, it will have a different W. I draw a third data set, it will have another W. And all these WJs, I want it to be sampled randomly. It's not just sampled from a fixed number of Ws, but finite set of Ws. But I wanted to draw it as random as possible. So in this case, I will be choosing a Gaussian prior for this W. Okay, so standard Gaussian prior. To model what we have seen in this in-context learning and in-context reinforcement learning case, I'm going to be creating this task where my goal is to ask the transformer to be given this xi, yi pairs I equals 1 through n, and this final test input xn+1, and I want the transformer to predict I want the transformer to give a prediction y hat on this last example. And I want this prediction to be a good prediction of the true label yn+1. Okay. So you can see this has exactly the same format as the in-context learning and in-context reinforcement learning problems we have seen. But now I'm doing it on linear regression. And pictorially, this transformer will be having this kind of architecture where you have x1, y1, x2, y2, up into xn+1, and then I'll be extracting the prediction from the output corresponding to the last token of the input. Okay, so I have like 2n+1 input tokens here. Since these are like just the real vectors, I don't need any kind of token embedding. I can just like directly for example, say using linear projection to project these vectors up onto the hidden dimension of the transformer. Okay, and then I can similarly use a linear projection to extract say a scalar output from this output token. Okay, so I can use the transformer to do this task pretty naturally. Okay, and of course the transformer, if it is not trained, it will not do well. If it is like GPT, maybe for GPT we'll do it to some reasonable extent. But in order to do a controlled experiment, here we look at the setting where we train our own transformer and we train a small transformer at the scale of a small GPT-2, but we train it on a massive metadata set. Okay, so we pull out about 20 million instances of this form. So about 20 million data sets, 20 million sequences, and then we use the standard square loss between this y hat and the true y to train the transformer. Okay, yeah, and then after training, we evaluate it on new test instances from this same setting. Before we see the result, it is important here to remember that in order to perform well, this transformer really needs to, on this task, this transformer really needs to learn about this Wj from the context, right? Since this Wj is drawn from a Gaussian prior, and we're in as long as we're in a reasonably high dimension, there's each time you'll be seeing essentially a new Wj that is not similar to any of the Wj you have seen before, right? So there's no kind of memorization kind of thing you can do for the transformer to do it well. Rather, the best bet for the transformer is to learn about this W from this sequence of training example xi, yi's. And after you learn about this W, you can apply your belief of what this W is approximately is. You can apply this W onto the new X to obtain your prediction. Okay, so your best bet is to really do this kind of in-context learning to recover this W. Okay, so this is really a task where you can test the in-context learning ability of transformer. And here's the result we have seen. Okay, so so in this blue curve, we plot the performance of the trained transformer. We're in this standard noisy linear regression problem. So by standard calculations, the Bayes we can obtain directly obtain the Bayes optimal predictor for this setting, which is just the ridge regression with a specific choice of the representation parameter lambda. Okay, so in this case, it will be the green curve here, and obtain that basically. And then here on the y-axis, I'm plotting the squared prediction error of either methods, and as you can see, perhaps surprisingly, the trained transformer can almost exactly match the Bayes optimal performance, right? And then and then this is pretty nice. So if you for example, if you modify the lambda in the ridge regression to like it's 1/10 or 10x, then the performance visibly degrades. Okay. And yeah, so and then I should mention that like this experiment, our first obtained in the prior works of Garg et al. And Akuri et al. Even though like this is this very plot is an experiment that we have done ourselves, but you can find similar results in these earlier papers. And also I should mention that here I'm just describing this problem in terms of a single sample size, capital N. So capital N is fixed here, but of course you can imagine that you can change this capital N, and you can make an x-axis of what is your number of in-context examples versus the performance. Of course, when your N is higher, you expect the loss to be lower, so performance to be better. And this is exactly what is done in this plot. Okay, so yeah, but yeah, like what we extract is that trained transformer really matches the Bayes optimal performance in this setting. Okay, yeah. Any questions so far?
A quick question here. So what we are actually learning here, because this is not a typical linear regression, right? The typical linear regression, you fix your W, right? Mm-hmm. So what we are actually learning here, are we actually trying to learn the coefficient come from Gaussian distribution? That's what we learn, or what we actually learn here?
Yeah, I think that's the exact question we want to like study here. So yeah, in order to do this task well, you want the transformer to learn actually a learning algorithm. Like the goal of the transformer is to accurately predict the y, and then you have to recover the w from the training examples in order to like accurately predict the final y, right? So the transformer has to do something to like recover the w from these and training examples. And there are many ways to recover the W, like for example, like by running like a gradient descent or like solving like matrix inverses. standard like running standard like ridge procedures. Yeah.
No.
So this is like
wait. Your WJ is different for each data points, right? So this is not a standard linear regression problem, right?
Right. This is not a standard linear. Right? Like you can.
You should be fixed.
Right.
You're learning the model, the linear model, or you're learning the randomness on.
Oh yeah, maybe yeah. So, but this is not a standard linear regression, right?
So there's a model AX plus B, and then there's the randomness that comes on top of the model. Because you got XIW, XJ, WJ plus noise. So what you have plus noise, and then
I see. Oh, okay. Sorry. I think I'm confused by the notation. So yes, your J is fixed. I see. Okay. So this is a standard linear regression problem. I see. Okay.
It's coming from a Gaussian model.
Yeah, but I mean, all of them are sharing the same weights. Yes. This is a standard linear regression model. So
sorry.
I'm confused by the superscript actually.
Yeah.
Okay.
Okay. Yeah. For those of you, and then I should mention here, like for those of you familiar with the meta learning, you can see like this setting is like just basically the same as meta learning. It's like, but then we're doing it in a different way. But like we're using a different model to solve it. Like we're using a transformer without any gradient update to solve it. But the problem setting is similar to meta learning, right? Like you want a procedure that's given like a few examples from a new linear model. You can quickly like make predictions on a text example, like make accurate prediction on a text example. So this is exactly like the problem meta learning trying to solve, or we're using a different kind of procedure, which is the transformer here.
Yeah.
Yeah. Okay. Any other questions about this setting? Okay, good. Yeah. So so this is exactly the concrete motivation of this line of work, which is why and how can transformers perform in-context learning so well in these kind of settings. And today I'll be talking about our results, trying to like answer this question. And I'll be mainly covering results from this transformers as statisticians paper, which appeared at NeurIPS last year as an oral. But then I'll also cover more recent results from these two papers called Transformers as Decision Makers and How do Transformers Learn in Context Beyond Simple Functions. Both of those will be appearing at iClear this year. Okay, but before diving into our results, I'd like to give a kind of a high-level perspective, which will be useful for us to think about these results. Is that basically transformers can implement learning algorithms in context, and then they can do it in an efficient way. Okay. So what I mean is that this transformer, though it is a generic sequence-to-sequence function that maps this input to this output, we'd like to think about this transformer as implementing some learning algorithm in this internally in its weights. So what I mean by learning algorithm is actually something pretty broad, is that any algorithm, any procedure that operates on a sequence of inputs, we can count it as a learning algorithm. So for example, gradient descent on an empirical data set, x, I, y, I equals 1 through n, that is a learning algorithm. And then we can use gradient descent multiple steps to simulate more complicated algorithms such as empirical risk minimization, right? Which is another learning algorithm. And then there are other kind of learning algorithms such as, for example, cross-validation, testing, as well as, for example, upper confidence bounds if you want to do bandits and reinforcement learning, right? So all of these, you can write it as some generic procedure that takes a sequence of X, Y as the input. And then we're going to think about all of these as learning algorithms. Of course, learning algorithms is nothing special. It's just a subclass of general sequence-to-sequence functions, right? But then I like to argue that this is not just some arbitrary sequence-to-sequence function, but it is an interesting subclass, and then it's actually a highly structured subclass of such functions. And adopting this view gives us more kind of a more informative and actionable perspective than some kind of more generic views, such as classical approximation theory, which just as transformers are universal sequence-to-sequence function approximators. Okay. So I'll give examples of what I mean by transformers to implement the learning algorithms now. Okay, so perhaps one of the most commonly used learning algorithm in machine learning is gradient descent. Here I have the formula for this algorithm when we're trying to learn a linear predictor on empirical data set of size n. Okay, so I have a linear predictor W times Xi. I have an arbitrary loss function L, and this is the form of the gradient descent on this linear predictor. What we can show is that as long as this loss L is smooth, there exists a single layer transformer with a mild number of heads that can approximate a single step of gradient descent. Okay, so what I mean is that this transformer, this single layer transformer is going to take this entire data set xi, yi, I equals 1 through n, as long as my initial point wt as its input. And then it's going to output a w hat that is going to be an epsilon approximation of the true next iterate of the gradient descent I just written here. Okay, and then to make it clear what I mean by the transformer to taking in all of these as the input, it's good to show here the input and output format of the transformer. Right. So transformer is a sequence-to-sequence model that takes a sequence of input vectors. So here I'm using a sequence of n input tokens, each of hidden dimension capital D, to encode this input. And the precise way I encode these inputs is I'll be going to put this n input data points x1, y1, and up through xn, yn in this location of each input token. And then I'll populate this location of each input vector with the same parameter vector, which is the initial point wt here. And then I'll use these remaining dimensions to populate other useful information that does not depend on the problem, but may depend on like other things such as the position, like for example, the positional encoding. I can think of it as additional information. I can put it over here in this part of the hidden dimension. What I'm showing here in this theorem is that the transformer is able to turn this input matrix to this output matrix, which looks the same, except that here, here where the transformer updates this W key thing with a new W hat that is the epsilon approximation of the gradient descent procedure. Okay, and to give some intuition of why the transformer can do this and then implement the gradient descent procedure on this part, observe that transformers are composing of this attention mechanism, can use the QKV mechanism in attention to retrieve tokens 3 times, right? So each of Q, K, and V can take inner product, can retrieve like a part of this input tokens. And then we can use this QKV mechanism to retrieve WT, XI, and XIs using the query key and value respectively. Okay, so for example, we can use the query to retrieve the W, and then we can use the keys and values to retrieve the XIs. And notice that this structure exactly resembles the structure we have here for the gradient descent on linear predictors, right? So here exactly we have the inner product between the WT and XI, and we have the multiplication by XI after the derivative is computed. So this exactly resembles the structure of the attention tool, where you want to take the inner product between the queries and keys, and then have some nonlinear mapping of this query key inner product after they are all computed, and then finally multiply by the value. Right? So using this a high resemblance of the attention mechanism and this gradient descent, we can use this attention to implement the dot product and nonlinearity, and then also implement the multiplication by the value vector. So using this structure, we exactly can implement this kind of procedure required in a single gradient descent iterate. Okay, and I should mention that here, in order to make this construction most clear, we have been used the we didn't use the standard softmax activation in the attention, rather we changed it to the normalized ReLU attention. And this activation has been also tried in the recent work on actual practical transformers. But our construction can also be generalized to softmax attention as well, but with a little bit more tedious arguments. Okay. So any questions about this? Okay. So that's one step of gradient descent. And then the next kind of straightforward realization is that once you have one step of gradient descent being implementable by transformer, you can easily stack these transformer layers to iterate an algorithm, right? So now by stacking all L of these transformer layers, you will obtain the following algorithm, which is just the L steps of gradient descent, right? But then this algorithm is a much stronger algorithm than a single step of gradient descent and can solve like many more problems. Again, since by the modularity of our input and output structure of the transformer we have just seen before, they can indeed be composed because the output structure of the previous layer exactly matches the input structure of the next layer. So concatenate them, stack them together, we obtain a transformer that is able to turn this initial point W0 to a final point W hat L, which is an approximation of L steps of gradient descent. Okay, sorry. So this is exactly what we show in this theorem, right? Like there exists an L layer transformer that approximates L steps of gradient descent, right? The only kind of non-trivial additional bit in this theorem is that the error accumulation is nice. So notice that here on the right-hand side, my error only blows up linearly in terms of the L. And then naively, this is not true. Like naively, you would obtain something that is exponential in L. But in this theorem, we additionally require the loss function is convex, okay, in its first argument. As long as the loss function is convex, then we can show that this error accumulation is actually linear in L. And the proof of this actually requires the kind of the stability kind of property, like of inexact convex gradient descent, in order to obtain this mild linear error accumulation. And indeed, if you're in non-convex setting, for example, minimize the non-convex quadratic, this stability breaks, and indeed this error accumulation can be exponential in the worst case. Okay, and then with this multiple steps of gradient descent at hand, we can finally construct our transformers to do in-context learning. Remember that this is the algorithm format of the in-context learning we want to construct a transformer to do. And we'll be using the similar input and output formats as the gradient descent, with a minor exception that now we not only have a training data set, we also have like the n+1 test data point, but we don't want the transformer to observe the y of the test data point. Otherwise, it will be cheating. So we'll be populating a 0 over here. But then on the output, we want the transformer to populate this location with the prediction y hat plus 1, n+1. Okay. And what we show is that there exist transformers that can approximate a wide range of in-context learning procedures. Here I'm showing ridge regression, logistic regression, so, but we can do much more, such as like gradient descent on two-layer neural networks. For all of these, we can our transformer admits a mild size. So the number of layers and the number of heads are all pretty mild. And for the transformer to guarantee like near optimal prediction risks under standard statistical models. Okay. So this is nice. So this kind of approximation theory argument, this kind of approximation theory result gives us some kind of justification of why these transformers can efficiently can do this in-context learning so well, right? Because they can, at least from approximation level, they can efficiently implement in-context learning algorithms, and then they can implement a pretty high accuracy version with a mild number of layers, right? So which gives kind of an answer to the question we were asking. And further, these size bounds on the transformer is further nice to allow you, which can allow us to do to obtain these generalization bounds, right? So, for example, by simple parameter counting, we can obtain this uniform convergence bound that says, if you have you don't see unlimited data, but actually you only observe n pre-training small n pre-training instances, then you'll have this uniform convergence result of the form like square root number of parameters over small n. Okay, and then you can connect these results with standard statistical results to obtain end-to-end prediction risk results, saying that if your theta hat is a pre-trained transformer on small n instances, then, for example, on a ridge regression problem, your excess risk will have this form, where this part comes from the generalization bound, and there's another part coming from like unavoidable statistical error with the optimal rate. Okay. Any questions here? So yeah, so these are some sample complexity bounds. And yeah, before we move on from this part, there's a like natural question here, which is that these are just the existential approximation results, right? Like this theorem only says that there exist transformers that achieves like these guarantees. Of course, you would ask, does this construction align with like actual transformers trained by gradient descent that we obtain in the experiments? While we did not give like we're unable to give like a full answer to this question, in the moment we will see some partial results in the experiments that test this question more like empirical settings. Okay, but before seeing those experiments, here's an experiment that just test the ICL performance. So yeah, so basically what we find in this, I won't go into the details for this experiment, but basically what we find is that the trained transformer can indeed perform near optimal in-context learning for many tasks, such as linear regression in both the noiseless and noisy versions, and sparse linear regression and linear classification. And the architecture we use here exactly corresponds to the architecture we used in our theoretical constructions. Okay, so yeah, we have this, as we just discussed, we have this question left, which is, what is actually the mechanism of the trained transformer? Like, does it align with our theoretical construction? And in this follow-up paper, we test this, we look at this question, and we actually consider a slightly more generalized setting of learning linear models on top of representations. Okay, so this is like, you can think of it as exactly the same setting as before the linear regression problem. Only minor difference is that now instead of linear on xi, we look at linear on some feature of xi, and then that feature map is fixed across all instances, right? So the feature map is not variable. Like the feature map is just one single mapping that the transformer can memorize, and then the rest is linear in context learning. Okay, again, we could have some theoretical construction of a transformer that does this task. Our transformer construct, I won't go into detail about this transformer construction, but it will consist of 3 steps. It will first featureize this xi into this p star of xi, and then it will consist of this moving step where it copies this p star of xi from this kind of what I call x tokens onto its onto the like subseeding token called the yi tokens. Okay, and there's some like theoretical reasons for theoretical convenience about like copying these phi stars into the onto the y tokens in order to like carry out the in-context learning procedure well. Okay, and then after this copying is done, finally we can use like we let the transformer to run linear in-context learning procedure to obtain the prediction y at each token. Okay, and so we have this construction, and what we do in the experiments is that we actually train transformers for these settings using the square laws as discussed before. And we'll do like this kind of linear probes on the trained transformers to look at what does the hidden states in the intermediate layers actually encode in these trained transformers. And what we find is the following. So so here are the linear probe results. What I plot on the x-axis is the layer index. So my particular transformer here has 12 layers. So I have index 0 to 12, where 0 is the input before the first layer, and then 1 to 12 is the output of the layer 1 to 12. Okay, and then for example, we can like zoom, we can focus on the red curve. The y-axis means the mean squared error of like linearly probing these hidden states, like linearly regressing these hidden states onto various quantities of interest. Like I can use linear regression to test whether the hidden states kind of contain certain quantities of interest. So for example, I can test whether these hidden states contain this featureized xi's, and I can ask this question for both the xi tokens and the yi tokens. Okay. And I can similarly, I can do like, I can test other quantities that, for example, like I can test the y hat obtained by ground truth, like oracle ridge regression using the phi star map. And what we find is actually a pretty strong signal. So for example, if you look at the red curve here, you can see like from layer 1 to 5, this error is dropping, and then it achieves the minimum at layer 5. So you can interpret this as, roughly speaking, this layer 1 to 5 of the transformer is kind of gradually performing this featurization process where they turn this xi into a phi star of xi. So the error of this linearly regressing this hidden states to get phi star of xi decreases, and it reaches the minimum at layer 5. Then from the second plot, we see like there's a sudden drop from layer 5 to 6 of the probing error at the yi tokens. And you can interpret this as suddenly after this phi star of xi have been computed at the xi tokens. And then at layer 6, it kind of does this copying mechanism where it copies the phi star of xi from the xi tokens onto the yi tokens, as we conjectured in the theoretical construction, right? So layer 6 kind of does this copying mechanism. And the this plus C probes the intermediate result, this ridge, this like y hat prediction from the oracle ridge regression, and it doesn't drop from layer 1 to 6, but it starts to drop from layer 7. Okay, and then it drops to a very low error at layer 12. So you can interpret this as, you know, roughly speaking, it looks like that layer 7 to 12 is doing some kind of ridge regression procedure to obtain, like to gradually refine the prediction to be closer and closer to the true ridge regression prediction, right? So roughly these plots can give you a sense that, you know, indeed these theoretically posited mechanisms that we obtain purely from like a theoretical approximation theory, they actually kind of like align with, or they actually emerge in the trained transformer, like actually trained transformers that we train via gradient descent. Okay. Yeah, so this gives some evidence about the alignment of the approximation theory and the real trained transformers. But of course, I should emphasize that this is a partial understanding only, and then in general, this kind of like linear probing and interpretability in general is a hard open problem that is like worth further investigation. Yeah. Questions here?
Yeah, there's a question in chat. Can you open the chat and
yeah, I have a question. Is this feature map learned or given a priori? So it is depending on, I think like if you in the perspective of the transformer, this is learned. Like this is a fixed feature map. Like you can imagine this is some, like, for example, like 3-layer NLP with some fixed weights, and this is shared across all the data instances. But the transformer didn't know it in the beginning. Like the transformer we train does not encode this implicit bias. Like they didn't know anything about this data distribution using this particular phi star. But using the square laws on the in-context learning problem, eventually it learns to kind of like memorize this phi star. Yeah. But it is not learned in context. Like it is learned kind of in weights. Like the transformer weights memorize this, but it is not need to be learned in context because all of the instances will share the same phi star. Okay, yeah, thanks. Okay, so yeah, I don't have much time, so I guess I'll just briefly talk about the capabilities beyond the simple algorithms. Previously, we have seen this trained transformer can behave pretty well. If you train it on linear regression, it can solve linear regression. If you train it on linear regression with representation, it can solve that. If you train it on logistic regression, it can solve that. What if we train the same transformer on the mixture of two kinds of tasks? Like what if the data batches consist of a mixture of regression and classification? And we don't give it any explicit prompting of which task it is in, right? Like just the two kinds of batches. For one kind of batch, XIYI comes from regression. For another kind, XIYI comes from classification. What would the transformer do in this setting? And what we find is that perhaps a little bit surprisingly, the transformer can solve both tasks nearly optimally. So this transformer called TF algorithm select, plotted in the blue curve, is able to match the optimal algorithm in both linear regression and linear classification, as if it can adaptively look at the data set and select the right algorithm. Okay, and then this is perhaps a little bit surprising and beyond what we have seen in the previous theory and experiments. And and then if you think about it, this kind of resembles what real human experts like statisticians or data analysts can do in real world tasks, right? Like you will first look at the data and explore it before deciding like which algorithm to run on this data. And we have the same result on the mixture of linear regression with two noise levels, sigma 1, sigma 2. Here, the two kind of data set is even harder for human eyes to distinguish because they look similar. It's just like a difference in the noise level. But again, like we can show that the training transformer, when we train it on the mixture of these two tasks, they can perform like ridge regression nearly optimally on both noise levels, as if it can select the optimal lambda for ridge regression. Right. So so to understand this phenomena, we kind of give these kind of settings, we kind of like term this capability in context algorithm selection. So it is kind of a kind of procedure. It's a kind of mechanism for in context learning, but it is beyond the mechanism we have seen, such as green descent or ridge regression for the existing problems. So, and then to be more concrete, what we mean by algorithm selection, we construct the two algorithm selection mechanisms and to give theoretical constructions to show both are implementable by transformers. We call this, both have a name, we call this first one post-ICL validation, and the second one pre-ICL testing. And I won't go into details, like you can think of this, but they're both like simple procedures for, if you think of it as a human experts, you can basically think of the first procedure as first running a train validation split, and then running K algorithms and using the validation loss to choose the one with the smallest validation loss. And this one, you can imagine it as a distribution testing procedure, where first has some distribution testing protocol, and then depending on the result, you run one of K algorithms to do the actual in-context learning. Okay, and then we can have some applications to use these algorithm selection mechanisms to construct transformers that can solve in-context learning with in more complicated statistical models that we have seen before. All right, and then finally, we have seen this example of in-context reinforcement learning before. I'll have this one slide which like describes this other follow-up paper also going to be appearing at iClear on like using transformer to do in-context reinforcement learning. And to recall that in in-context reinforcement learning, the goal of the transformer is to give an interaction history with a new environment output an action of high quality. And we provide a theory for in-context reinforcement learning with transformers. What we show, the key thing, which is parallel to the ICL thing we have seen before, is that here our construction of the transformers is that they can basically be implementing various reinforcement learning algorithms in context, right? Which is also a sequence-to-sequence function that maps this entire interaction history, which is the input, to a high-quality action, which is the output, and then the internal procedure it will be implementing is its various RL algorithms. And then examples include, for example, linear UCB or time sampling algorithms for bandits, as well as UCB value iteration algorithms for tabular MVPs. And the proof specifically for UCB value iteration utilizes attention mechanism efficiently to do things such as tabular visitation counting, as well as using backward dynamical programming to do the planning. Okay, and then we also give a statistical analysis of such transformers. You can show you can use simple supervised imitation loss, which is just the next token prediction loss on a data set of this form. On certain offline data of high quality defined in a certain precise sense to learn our algorithms. Okay, and then you can show this, for example, when you deploy this training transformer as an actual RL algorithm in online environments, the regret of this training transformer will be close to the regret of the nominal algorithm you're imitating, up to a small additive error. And then you can achieve this epsilon error with polysamples in our epsilon and other problem parameters. And as special case, this provides the first statistical guarantees for a number of known training methods for in-context reinforcement learning, such as algorithm distillation and decision pre-trained transformers. Okay. Yeah, and then before we wrap, I just want to mention that there's a growing body of work on understanding transformers through in-context learning, and then our work just fits into this broader body of work, which has been growing very fast in the past 2 years. And then there are many like other exciting results that look at this problem from other perspectives or provide other theoretical or experimental results, and which are all like pretty interesting. Okay, so to summarize, in this work, we give a comprehensive theory for in-context learning, covering the approximation power, the generalization bounds, as well as like the in-context like statistical performance for transformers to do like various in-context learning problems. And throughout this theory, we use the perspective of transformers can actually efficiently implement learning algorithms in context. And we also identify new capabilities such as algorithm selection of the transformers. And finally, we conduct some experiments to show some preliminary results about the alignment of the transform mechanism, trained transform mechanism versus and the theoretical constructions. And there are many like exciting open directions in this line of work. For example, like is there more kind of a unified theory for algorithm approximation using transformers? Like, is there some sort of complexity measure of an algorithm that we can define such that characterizes approximability by transformers? Some further studies of the internal mechanisms, both in in-context learning settings or in-context RL, or in like more general settings, which would be, for example, like a similar line of study can be found in this kind of physics of LM work by Zeyuan and Yuanzhi. And finally, some non-convex training dynamics of transformers, which we haven't been touching in this talk. We only like give approximation theory and generalization results, but we haven't touched the training dynamics of non-convex gradient descent for learning the transformers. But people have studied this. For example, the work of Richie Zhang et al. At Berkeley, they did this on linear ICL. And then there's also a bunch of work that does this beyond the ICL setting for transformers. And this is definitely like worth understanding. And this is also related to the non-convex training dynamics is also related to like more practical questions such as like scaling laws. Yeah, and finally, I think like in-context reinforcement learning is a very exciting like empirical direction. Getting transformers to do like in-context reinforcement learning well in like unseen real world experiments. Like there have been some recent work that does it on like hard environments such as like open world Minecraft, and how to even scale that up further is like an interesting question. So yeah, with that, I'll conclude here. And yeah, thanks for your attention.
All right, thank you very much. Questions from the audience? And from people online also? Yes, go ahead.
You did the study on a linear model, but what would be your expectation if it wasn't just a linear model you're trying to learn? Let's say a sinusoidal or some more complex model. What would be your expectation about the prediction?
Yeah, that's a good question. I think like, so we like for this talk, we focus on linear problem, but so actually in the like work of Garg et al, they did some nonlinear models such as like 2-layer neural network. Like if this is not a linear model, but a 2-layer neural network. In that case, certainly like you won't fully recover the neural network. Like I think what they show is the transformer can only match some suboptimal algorithm, such as like a few steps of gradient descent. But like it is also unclear like what the optimal algorithm is in that, or like it's computationally maybe intractable to implement the optimal algorithm, like which is the Bayes predictor. But like what they show is that the trained transformer can match like a few steps of gradient descent in that case. Yeah, and I always expect like it to be like similar for other things such as like, for example, sinusoidal. Like maybe if the transformer does not have the capacity to run like optimal learning procedures for that particular nonlinear model, maybe at least it is able to imitate some weaker learning procedures, such as like a few steps of gradient descent.
The big question is the attention mechanism is that the transformer is providing, is giving you the general learning capability compared to, let's say, a linear regression or a nonlinear regression. In nonlinear regression, we're trying to kind of fit something. But in here, you have the attention mechanism. And is the attention mechanism is able to kind of learn not just linear relationship, but nonlinear relationship. And I think this is what the transformers are trying to capture, right?
Yeah. That's a good question. I guess if I'm understanding correctly, they do have the ability to implement. Like for example, here I'm showing like if you scroll to here, we use the attention mechanism to like simulate green descent on linear predictor. But imagine like if this L of like WXY is not like a linear predictor, but some like nonlinear thing, then I would say like in general, as long as this is not like some degenerate thing, it is some regular, like for example, neural network or some other regular nonlinear model. I would say like the attention mechanism will still be able to implement it, but it will be like less efficient. Like for example, if this is a two-layer neural network, maybe you need like much more number of heads or even much more number of layers to simulate a single gradient descent step. So the efficiency is like the key distinction. Like if you're given enough number of attention layers with enough number of heads, I think like for most like standard nonlinear models, you should be able to implement at least gradient descent on that model. I'm not sure about like other learning procedures though, but yeah.
Thank you.
Yeah, so this actually has to do with the question I was asked. So how special is this architecture? Because your argument is this is from approximation theory point of view, right? So if I replace this with just a multi-layer perceptron, is it everything is doable, or you see some barrier there?
Yeah, that's a good question. I think the answer is similar to the previous answer, is that I think the efficiency is the key. Like the key is not like whether it's doable or not doable, but the key is like the efficiency in terms of like the number of layers and number of parameters, number of heads, etc. I think with an MLP, like you can definitely implement the same gradient descent procedure. But for the MLP, the number of parameters will be proportional to the sequence length or even the proportional to square of the sequence length. So like it will be like much less efficient, and then the generalization bounds of the MLP will also be like much higher than the generalization bound of the transformer. Right? Like just for the transformer, the number of parameters is independent of the sequence length. Yeah, and then there's the similar question. You can also ask it for RNN and RSTM. Like so that would be like a slightly different story because the RNN and RSTM is also parameter efficient. Like it does not depend on sequence length, but the representational power of the, at least for implementing gradient descent, the representational power of the RNN and RSTM is not as good as the attention, because the attention can basically like have memory to retrieve, like have this mechanism to retrieve all past tokens xi. Whereas if you have like RNN or RSTM, then basically you only have a single state vector to encode all previous information. That things that are not stored in the state vector is lost. So using RNN and RSTM will also cause some troubles. Like it will be not as easy to do the approximation argument as in this theorem.
Yeah, so yeah, a related question is, so for slightly more complicated algorithms, I mean, this one is a gradient descent, right? If you implement slightly more complicated algorithms, like for example, some second order methods, so do you see this is appropriate or this architecture?
I think second order is fine. Like you will be using some like you can still use like first order as like subroutines for the second order procedures. Like for example, you can use a bunch of gradient descent steps to, or like I don't know, like for example, like accelerated gradient descent or preconditioned gradient descent to simulate things like Newton steps or like trust region steps.
Yeah, we can definitely in that way. Yes, yes.
Yeah.
So there's one question in the chat talking about in a plot for regression with classification tasks, is there a double descent phenomenon for one of the noise level?
Yes. So yes. Yeah, that's a very acute finding. Like you can see here, there's basically you run like when your regularization parameter is smaller than Bayes optimal one, this orange curve, there's a slight you can see there's a slight trace of double descent. Even if you decrease this lambda even more, you will see like a clear double descent. this is nothing about the transformer. This is just like running a regression with some lambda on a linear regression problem where the optimal lambda is some other lambda. So if your lambda is too small, you will have double descent. If you're unregularized, then you will have like this. Your double descent will go to infinity.
Any other questions?
Yeah, I have a quick question here. So this instance regression task, would you say it is dependent on the sequence in which the data is fed in? So if I apply a fixed permutation of the this data set and then feed into the transformer, do you think you will get the same efficiency or you can match the Bayes optimal performance?
You mean in this setting, in the linear regression setting?
Yes.
Well, I don't think the permutation changes. You mean like do you mean you permute xi yi, or do you mean you make y not match with the x?
Like 2n plus 1 points here, right? You just apply a fixed permutation for each data point and you feed into the.
Oh, you mean like permute among the coordinates of the x?
No. Between xi, yi, just any random permutation. For example, you
mean like permute like so 1 through n to some like permuted order.
Yeah.
That won't change anything, I guess, because these are all IID.
Yeah, my question is, will the architecture of transformer depend on that positional encoding or not?
Oh yeah.
Yeah. So
yes.
So you mean you permute the positional encoding? I think if you permute the positional encoding, then there will be some problems.
So because we input 2n plus 1 input token, right?
Yes.
So his point is that if we random permute the tokens, 2n plus 1 tokens, will the result change? Because if you apply positional encoding, obviously if you random permute the input, there's some changes, right?
Position matters.
I mean, like if like the thing I've written here is like I'm like omitting the positional encoding. Like you can think of the TF map as like the position encoding is part of the TF map. Like these x's don't include the position encoding. So in this case, if you permute the x's, like it doesn't matter because these are just like ID. But once let's say here yeah. So let's say here, let's say my positional, like let's say we consider this input where this one includes the positional information. If we permute like these guys, like if we permute these full hidden vectors, then I think here it is still fine because like this one, like actually for the construction of this one, it is like it's still invariant to like this location. Like I just want this WT to be like there's no token that is special one. Like for this green descent construction, this one is fine, but for in-context learning, there's some like asymmetry. Like for example, like you see here, there's the test example appears at the last location. Well, I still think the XIYI equals 1 through n themselves, they're like symmetric to each other. So yeah, I would say now I don't see any issues like permuting these ones, including the positional encodings.
Okay. Any last question? People online?
Great.
All right, let's thank the speaker. Okay, thank you. I'm going to meet you in about 10 minutes.
Okay, yeah, thanks.
Thank you.
Yeah, thank you.